magnesium chloride. And the chemical formula for this is MgCl2. Now we're going to determine percent composition. Again, you're going to have to use the periodic table to determine mass. We're going to look at baking soda for our example. Okay, remember baking soda is NaHCO3. So I need to find the total mass of Na, H, C, and then 3 times oxygens because we have this 3 subscript right here. Okay, sodium has a mass of 23.00. Hydrogen has a mass of 1.01. Carbon has a mass of 12.01. And 3 oxygens have a mass of 48.00. When you add these together, (84.02) is your total mass. Now I'm going to do the second part, which is part divided by total times 100%. I'm going to do 12.01 because that is the mass of carbon, divided by 84.02 times 100%, which gives me 14.29%. So the percent composition of carbon and baking soda is 14.29%. So I'm going to look at the periodic table. Na, H, C, and O. The next thing we're going to do is balance equations, and the PowerPoint did not transfer correctly into this program. So the first equation that we're going to balance is sodium phosphate and potassium hydroxide. So I've got Na3PO4 plus KOH yields NaOH plus K3PO4. Okay, starting at the beginning on the left, I've got 3 sodiums. Well, I only have 1 sodium on the right, so I'm going to put a 3 right here. My sodiums are now balanced. Next, phosphorus. P's. I've got 1 on the left and 1 on the right, so I'm good. Next is oxygens. I've got 4 plus 1, which is 5 on the left, and then 3 plus 4, which is 7 on the right. So I need to balance that. Since I've got my sodiums balanced already, I'm going to put a 3 in front of the KOH, which makes oxygens 4 on the left, and 7 on the left and 7 on the right. Then I get to K potassium. I've got 3 on the left, 3 on the right, and then I've got 3 hydrogens on the left and 3 hydrogens on the right. So this one is balanced. Next example, MgF2 plus Li2CO3 yields MgCO3 plus LiF. Okay, I'm going to start with Mg. I've got 1 on the left and 1 on the right. Next is F2. I've got 2 on F. I've got 2 on the left and 1 on the right. So in order to fix that, I'm going to put a 2 here. Then I've got Li, I've got 2 on the left, 2 on the right. And then C, 1 on the left, 1 on the right. And O, 3 on the left, 3 on the right. So this one is balanced. Okay, last example, P4 plus O2 yields P2O3. Okay, I've got 4 P's on the left and 2 on the right, so I'm going to put a 2 here. That makes both sides 4. Then I have 2 O's on the left and 6 on the right because 2 times 3 is 6. So I need to put a 3 here in order to balance that equation. Okay, next we're going to look at drawing a Lewis electron dot diagram. I found these steps online. Steps to drawing an electron dot diagram. First, write out the chemical symbol. Then find the number of valence electrons. Now, valence electrons are the number of electrons in the outside shell. In order to find the number of valence electrons, we need to look at the periodic table. So now that you know the number of valence electrons, you're going to draw the valence electrons in the following configuration. Since 8 is the magic number, you draw the electrons in sets of 2 in sort of a box like this around the chemical symbol. Now, depending on how many electrons are in the shell, depends on how many dots you're going to draw. Chlorine has 7 valence electrons, so there's only 7 dots around it. If you look at the periodic table, the columns indicate the number of valence electrons. 1, 2, we're going to skip the middle section, 3, 4, 5, 6, 7, and 8. Since 8 is the magic number, 8 is stable. It's like a happy place. This is because it has the lowest energy state when the electrons are in this configuration. All atoms, compounds, molecules strive to have the lowest energy. Okay, last we're going to compare the electron configuration of molecules to a stable noble gas. Now, I honestly, as any good pre-AP chemistry student, had no clue what this was talking about. So I went to my handy Google app and I found this, chemical bonding. Chemical compounds are formed by the joining of 2 or more atoms. A stable compound occurs when the total energy of the combination has lower energy than the separated atoms. The bound state implies a net attractive force between the atoms, a chemical bond. Okay, so that helped me out a little bit. Just a little bit further, and I saw the noble gas rule, which states that every atom in a molecule seeks to attain a noble gas electronic configuration around it. Okay, well that makes sense too because 8's the magic number. After researching a little further, I came across the octet rule. The atoms that participate in covalent bonding share electrons in a way that enables them to acquire a stable electronic configuration or a full valence shell. This means that they want to acquire the electronic configuration of the noble gas of their row. Now, obviously, the name of this rule is a misnomer because helium, the noble gas of the first row, only has 2 electrons, and hydrogen, the only element in the first row besides helium, fulfills the octet rule by sharing 2 electrons only. So, what I'm looking at is looking at molecules and seeing what noble gas it is that they're trying to look like. If I look at the periodic table again, these concepts allow me to predict the molecules made of non-metals and which gas they want to be. If I first look at water, which is H2O, oxygen is right here in this row, and the bonding of the 2 hydrogens together allow oxygen to now have the valence electron shell the same as neon, which makes it very stable. Another example is carbon dioxide. Carbon is here, and it attaches to 2 oxygens, which gives it the valence electron shell of neon. Again, another noble gas, so it's very stable. And the last example is a metallic bond, FeCl2. Now, Fe, which is iron, my favorite element. Where is it? And chlorine. Now, we only want to look at the non-metal. The chlorine bonded to the iron fulfills the octet rule for the noble gas argon. So the noble gas that it wants to be like is argon. And that completes our review. Study hard and do good on your final.